Okay, so 2010 PC1 Form B. Alright, so let's check it out, see how we did. We got a graph here of a curve, and we have this line here at y equals 6. So that point 0, 6. This point down here is 2, 0. And the shaded region we have is the top part up here. And it says that the graph, that is the curve here, is y equals 4 ln of 3 minus x. And the horizontal line y equals 6, vertical line x equals 2. Find the area of the region. So ultimately we got essentially a couple choices here to find the area of this region. One choice would be to find the area of this white part, which would ultimately just be the integral of this. Okay? And subtract it from the area of the rectangle. Would give us the colored part. So again, if we wanted to do it that way, we go 0 to 2 of 4 ln 3 minus x dx. And again, that would give us the area of this part. And from that, like I said, we could subtract the area of the rectangle, which is ultimately a 6 by 2 rectangle, would be 12 total. So if we did that, would be a very reasonable way to do it. So let's go with that plan. So if we do our math 9, 4 ln 3 minus x. 4 ln 3 minus x. There we go. And comma x, comma 0, comma 2. Get that result. So 5.183. And if we go 12 minus that, we get our answer. And so final should be 6.817. Any questions on number 1? Keep in mind that we also could, since we have a top of this vertical line and the bottom is the natural log function the whole time, could we have also set up from 0 to 2 of the top function, which is 6, minus the bottom function, which is 4 ln of 3 minus x. 3 minus x. Would that have also worked? Think about why that works too, just from the geometry of this. If we were to anti-differentiate this, wouldn't we get 6x? If we put a 6, if we put a 0 and a 2 in there, the 2 would give us the 12, wouldn't it? So ultimately, wouldn't it be 12 minus whatever we get for this? So it's really the same problem, just written in a different format. All right, 2 points. One for having the correct integrand, one for having the correct answer. 2 points for that one. All right, so move on to part B then. Part B says find the volume of the solid generated when revolving R about the horizontal line y equals 8. So we're going to take that region. We're going to revolve it around a line that's above it, up here at y equals 8. Okay. And ultimately, since we do have a top and bottom that's the same throughout the region, if we were to make a vertical slice here, then the vertical slice would be perpendicular to the revolving line, which means that we would get either discs or washers. Since there's a space here, we would certainly get washers. So if we set that up correctly, 0 to 2 pi, we need the outside radius squared. And remember, keep in mind the outside radius is this. How far is it from the outside of the washer to the revolving line? Well, ultimately, this right here, that distance right there would just be the ln x curve, wouldn't it? 4 ln of 3 minus x. And so how far would it be from here to here? It would be 8 minus 4 ln 3 minus x. So again, that expression right there would represent the distance from the revolving line to the outer part of the washer. And squared, of course. And then the inside radius of the washer is this. And ultimately, what is this? No matter where we are in the region, that distance right there is always what? It's 2. It's just the difference between 8 and 6. So we have 2 squared dx. And so, if we set up our washer method correctly, calculate. We get 8 minus 4 ln 3 minus x. And that's all squared. Minus 4. We get that. And keep in mind though, that's just the area part. We still have a pi out in front, so it's that times pi. Whoops. And if we do that, ultimately I should get 168.179 or 180 actually. So a 5 behind the 9, so 180. Alright. Okay, 2 points here for having the integrand correct. So if you got the outer radius, inner radius correct, 1 point for each of those, and then 1 point for having 168.180. And remember again, just keeping in mind that if we were to round this wrong, in this case, the AP test allows for either rounding up or truncation. So if we put 179 here, that would be okay on the AP test. Our general rule in this class is always round up, but ultimately the AP class allows for people that truncate, so we could take the 9 and just cut it off and have it be 179, and that would be okay. But if for some crazy reason you put 181 here, okay, you're going to lose the answer point. Okay, it's got to be exactly right, either the truncated version or the rounded correctly version, but if you got even off by 1,000, you'd lose that whole point. So make sure you're careful on your rounding and so on. Don't use rounded answers to get new answers and so on. Okay, any questions on the setup on part B? Alright, let's see if we can do part C here. We got this time we have, it says this region is the base of a solid. For this solid, each cross section perpendicular to the x-axis is a square. Find the volume. So once again, got a problem where we have, if we take a slice here, perpendicular to the x-axis, and remember that it's tough to draw in 3 dimensions here, but ultimately that comes out at us, it comes out of the paper at us as a square. Okay. And the base of the square is in the region, so as we move from left to right here, these squares are going to have different areas, but ultimately the general idea here is to write the area for the general shape, which the shape of each slice is a square. So we know the area of the square is A equals S squared. And the question is, can we come up with an expression for the side length of that square? Well, the side length of the square is just going to be 6 minus 4 ln 3 minus x, isn't it? So if that's the side length, then what's the area of that square? That squared. So again, ultimately, all we're looking for is an expression that'll give us the side length of that square right there, and the one that we've drawn. And how do we find the areas of all the squares together, which ultimately makes a volume? Integrate it from what to what? 0 to 2 dx. And if we pump that in the calculator, should get 26.667. 2 points there also for the integrand, 1 point for the answer. And you might, if you did the math on that, that was only 8 points. Okay. So the other point is for having the correct limits for each of these. So if you had the 0 to 2, 0 to 2, and pi, you get an extra point. So bottom line is if you got all 3 answers right, then you're pretty much going to get the extra point then. Huh? Right. So correct limits, the 0 to 2 and the pi, 0 to 2, and then the 0 to 2 for these 3 parts. Okay, if you add all that, 1 more point for that. Okay, any questions about part C? Okay. Let's carry on then. Number 2. Number 2 looks like a BC problem because we have parametric derivatives here. So we ultimately are going to have 2010 Form B, BC2. And for number 2, number 1, or part A, it gives us a velocity vector here, gives us the velocity components from the x direction and the y direction, gives us a time frame 0 to 1.5, and it also gives us an initial position, time 0, the particle is at the point 2, negative 2, 3. And so for part A here, our job is between 0 and 1.5, it says find all the values of t at which the line tangent to the path of the particle is vertical. So again, this curve, remember, is whether it's defined in parametrics or not, the derivative of it is still dy dx. Because ultimately the position of the particle is going to be determined by the x and y coordinates. Okay? And we could draw it on an xy plane, and each time would correspond to a particular point. The bottom line here is we need to know something about dy dx here. Well, we learned that dy dx is equal to dy dt over dx dt with the parametric equation. So ultimately my dy dt is 1 plus sine 2 sine t squared. And on the bottom we'd have 14 cosine t squared sine e to the t. This is when you're thankful that it's a calculator problem, right? Alright, so ultimately that would be our dy dx. And the question says find all the values of t at which the line tangent to the path is vertical. Well, if the line tangent to the path is vertical, that means that 14 cosine t squared sine e to the t would have to equal what? That would have to equal 0. Okay. Alright, so if we set that equal to 0, let's see what we can find here. We know that in our window here we were only going from 0 to 1.5. We'll go negative 5 to 5 on our y direction. See what we see here. Equation that we got, 14 cosine x squared sine e to the x and looks like we got 2 possibilities there, looks like. So, if we want to find them, we will go ahead and use our 0 command. Get ourselves over there by first 0. And looks like we get 1.445 would be one of the solutions. And the other solution? Would be 1.253. Alright, so ultimately 2 points. One if you set the bottom of the derivative equal to 0, and one if you found the 2 answers. Questions? Okay, let's see what we got here in the next part. And part B, we have to write an equation for the line tangent to the path of the particle at time 1. Right? So ultimately, if we're going to write the equation for any line, we could we'll start out with our point slope form as normal. Okay. And let's see if we can find a point and a slope. Well, the point is going to be determined by the x and y parametric equations they gave us. No, because those are not the positions. Those are the velocities they gave us. And those are the derivatives. So we'll deal with that in a minute. Let's see if we can find, we already know what dy dx is though. We know dy dx is 1 plus 2 sine t squared. And the bottom 14 cosine t squared sine e to the t. So we know this is dy dx, so that's going to be able to tell us what our slope is, which will be our m in our equation here. So if we put in a 1, we're going to get, again, not exact answers here, so it's a calculator problem. So let's go ahead and figure out what that is. And ultimately, if we want to evaluate this at 1, we could put 1 in there and do it all separate, or we could just use the table here. So I'm going to do the table version. So we'll do 1 plus 2 cosine x squared divided by, oops, yeah, this is 14, that stuff on the bottom. So, and this one here. Did I have that backward? No.
On the top, sine.
Oh, sine, not cosine, thanks. There we go. So 1 plus 2 sine x squared looks good, right? 14 cosine x squared sine e dx, I think we're good. And if we go table set, it's already on ask, so type in a 1. Looks like we get 0.863. So that would be our m, if you will. Alright. Now, the other issue is, what about the point? How do we know the location at time 1? Alright. Well, remember they gave us the location at time 0. True? And so to get the location at time 1, it's ultimately just a displacement problem, isn't it? Okay. So remember though, with parametrics though, we got 2 different variables to worry about here. We have to find the displacement in x and we have to find the displacement in y. So ultimately our position, if you will, at time 1 is going to be found by doing -2, which is our position at time 0 in the x direction. Okay? And we're going to add to that the displacement from 0 to 1 of dx dt dt. Okay? So that will give us our position of the particle at time 1. The position at 0 is -2, and if we add that to the displacement, okay, then we're going to have our new position at time 1. So, with that said, we do our integral here. And just for, I guess for time's sake here, I'll just tell you what you get here instead of typing that all in there. But bottom line is you can type that in there without too much trouble. But ultimately the final answer here for the position is 9.315, the nearest thousand. And then again, remember, since it's a x and y situation, 2 different positions to worry about, an x position and a y position. We do the same thing here, 0 to 1 of dy dt, which ultimately gives us the displacement in terms of y. And if we do the math on that, we're going to get 4.621. And so that ultimately is our position at time 1. That's our x coordinate time 1 and our y coordinate time 1. So final answer then is y minus 4.621, 0.863 times x minus 9.315. And how many times out of 10 should we solve this for y? 0. How many times should we put this in standard form? 0. Okay. Just leave it in point slope form, call it good. Alright, so point breakdown here was finding the derivative at 1 was worth a point if you found the correct derivative. If you found the 2 coordinates, 1 point for each of those, and then 1 point for putting them in the right answer. And again, I'm pretty sure we've discussed this before, but just for argument's sake, let's say we made a mistake here and we got whatever we did, maybe we typed it in wrong and got 8.426. Okay? So we would not get this point, but could we still get the final answer point here if we used our 8.426 or whatever in there instead? You bet. Okay? So, like I said, you just can't. One thing that you can't do, you can't just say they won't give you points for trivial stuff. Like if you just had no idea and you wrote x of 1 equals 2, just out of the blue, you just picked a number, and then you use that to get this answer, then they would say, no, sorry, you lose all 3. But if you do most of the work right and you get some answer wrong for some reason, and you use your wrong answer here in this final point part, you could theoretically, as long as you did the last part right, you could theoretically get a point for that. Okay? So try every part. All right. Any other questions on part B? Okay, part C then asks us for the speed of the particle at time 1, and we know that the speed of the particle is the absolute value of the velocity. Okay. And in terms of having parametric equations, the absolute value of the velocity is the square root of the 2 derivatives squared added together, or the square, yeah. So dx dt, dy dt. So we know that's our speed. And so for us, if we were to plug those dy dx, or dx dt and dy dt, plug both of those in there. And keep in mind this is at 1, so we'd be putting 1 into these and then squaring those numbers, because we're going to get a number when we put the two velocities in. So number in here, squared, added together, square root should turn out to be 4.105. And 1 point for getting the speed correct. Questions so far? All right. Final part, part D, how about the acceleration vector? Well, we know the velocity vector here. The acceleration vector, of course, is just going to be the derivative of the two acceleration components. And since they're asking for us the acceleration at 1, okay, do we really even need to write anything down? Aren't we asking for a derivative at a point for each of these? And what do we have in our calculator that gives us derivative at a point? You can sit and do it by hand if you want to, but ultimately that's a calculator problem, so you don't need to. Recognize that all they're asking for is the derivative of the velocity at a point. Velocity for the x direction is cosine, 14 cosine x squared. Oops, wrong button. Squared. And then sine e to the x. So we just want the derivative of that x component at 1. Gives us negative 28.425. And the acceleration in the y direction. 1 plus 2 sine x squared. That at 1 is going to be 2.161. And ultimately 2 points, 1 for each. So ultimately this would be more difficult if it was on the non-calculator part, because you'd have to actually find the derivative by hand, which is doable because it's just product rule on one of them and product rule, chain rule. Okay. So you could find the derivative and plug in 1 and find those answers, but it would be pretty difficult to come up with the decimal approximations, of course, if it was on the non-calculator part. So if it were on the non-calculator part, it would give you functions that are easier to deal with, of course. Questions on that part, or any part of number 2?